What we're going to be talking about today is nanotechnology. I've been working on nanotechnology for a long time now, and I'm co-founder of Foresight Institute, which is a nonprofit. We do the nanotechnology conferences and the Feynman Prize in nanotechnology. Okay, so we're going to do a very quick tour of nanotechnology today. The goals for this session: we'll do an introduction. We're going to look at the long term of nanotechnology, what is the most ambitious limit this technology can take us to, which is atomically precise manufacturing. And then the next speaker is going to look at some very exciting commercial opportunities. So first, to get a little oriented, these three objects are 1,000 times different in size. We've got DNA, 1,000 times bigger is a bacterium, 1,000 times bigger is a large raindrop. These objects are 100,000 times different in size. We have our single-walled carbon nanotube. 100,000 times wider is a strand of your hair, and then another 100,000 times wide is a house. And finally, now we're getting into the millions. A nanoparticle on the left, 1,000,000 times bigger would be an ant, and another 1,000,000 times bigger would be a racetrack. But is it really about length? The real world isn't so much just about length. Length is just in one dimension. Area is a square, flat surface. A lot of physical things depend on area. But real things, physical objects, are about volume, 3 dimensions. So in what is nanotechnology, a nanometer is about 1/1000th of a meter. It's exactly 1/1000th of a meter. So nanotechnology is just short for nanometer technology. The US government has a definition it uses for nanotechnology between 1 and 100 nanometers in length, which gives us between 1 and 10,000 square nanometers in surface, or 1 in 1,000,000 cubic nanometers. So a factor of 1,000,000 in volume here. So how do we get a grasp on this? Let's blow them all up by 1,000,000,000 so we can really get a feel for this. Instead of nanometer technology, now we're talking meter technology. So the range of dimensions this technology has go from between 1 cubic meter at the smallest size to 1,000,000 cubic meters on the high end. So when you picture this, it's everything from a box about the size of a yard in dimension on each side, for those of us who still think in English units, and on the high end, a box which is 33 stories high, about as high as the building we're in, and 33 stories wide, 33 stories deep, a gigantic building. And no specification of what's in those volumes, none at all. So meter technology could be anything in any size box. It could be a rock in the smaller box. It could be a small mountain in the bigger box. It could be a butter churn made of wood, a Tesla vehicle, a roboticized factory. All of these would be meter technology. So is nanotechnology a coherent technology? Not under that definition, no. It's not a useful term for our purposes right now. Now, of course, there was a reason why they used this term. It was a government definition. They wanted to make sure it covered anything they might possibly want to fund. And it does that really well. But what we're going to do with this is, we're not finding this useful, so we're done with this definition. Let's just look at some cool technology. Okay, so 3 useful categories of nanoparticles that I like to think of. One is nanochunks. They're just like a small rock. Nanoblobs, if you see that one that says shell down there, this is a spherical thing. It's got some kind of coating. The stuff on the inside is supposed to dissolve. They do vitamins this way. So a nanoblob would just be something that's temporary. It's supposed to dissolve, often in your body. But the most interesting one are the nanoshapes. And you see some pictures here. You see some spheres, and you see some tubes. You see these flat things that could slide across each other. Here's the soccer ball molecule. Now, this is a very international conference. Let's call it the football molecule. So we have Buckminster fullerene is the nickname for this, and the buckyball. Each black thing is a carbon. It's a carbon atom, and those are the bonds between them. It looks like a sphere. It's very, very much like a sphere. You can imagine these things rolling around. They make fullerene-like spheres and shapes out of tungsten disulfide that make nanoscale ball bearings that roll in lubrication. Now, if you look at this, look at the red thing, that long red tube. You're at a very small scale now. That's a carbon nanotube shown in red. These long tubes made of carbon are extremely strong and have very interesting electrical properties. We'll be looking at some of the results of that strength. Very exciting. Now, these are relatively big nanoballs that have a lot of platinum in them. They are grown from a smaller piece of protein. If you put these in water and shine light on them, they can liberate hydrogen from the water. Now, those of you who know how useful hydrogen is, we're looking forward to a hydrogen economy. We have to make this stuff. Yet we can get it from water using these. These are quantum dots. They're semiconductor nanoparticles. You can tune them to specific light frequencies, and then that makes your solar cells be able to absorb much better at different frequencies. These are molecular sieves called zeolites. They have millions of nanoscale pores, and you can see these molecules flowing through the pores. As they do that, aluminum ions that are stuck in there cause catalysis. They cause a chemical change that can do oil refinement. Now, we mentioned hydrogen and making hydrogen. We all want the hydrogen economy. We want hydrogen cars. In order to do that, you have to store that stuff safely and efficiently. If it's not stored safely, it explodes on you, right? And if it's not efficient, your car won't go because it's too heavy. So here would be a metal organic framework that would enable you to store that hydrogen and hopefully be able to have our hydrogen cars. Of course, what we really would like are some wonderful medical technologies. This is something that's being worked on very heavily by the US federal government in terms of funding cancer nanotechnology. You see on the left there's that red spot. Let's say that's a cancer. You see these green nanoparticles functionalized with some kind of medication being sent into the body. They home in on the tumor. This is what you need for effective cancer treatment. Right now, this cancer treatment goes all through your body and your hair falls out, right? That's one of the big effects. We want it to home in on that cancer. Then you can image it. Hopefully they kill the cancer cells and you end up without cancer. Now, I got a little preview from our second speaker who told me some sad news that a couple of the clinical trials in this are not working out. But I am determined that I believe this is going to work because they're throwing so much money and so much brilliance at this problem. A couple products that are already out. Somebody had the idea to put these buckyballs in face cream because they're a strong antioxidant. But of course, anything that goes on women's faces ends up in babies' mouths, right? Is this a bright idea? Have these things been tested? No, they have not. Possibly not a brilliant concept here. Samsung, a very well-respected firm, decided that it would advertise silver nanoparticles in their washing machine water. They said they were releasing silver nanoparticles in the water. But again, the first thing you think of is, wait a minute, doesn't that water go out into the environment eventually? And yes, of course it does. So what's the effect of that? Well, it's unclear. And so perhaps not the most thought out plan here. Now, there are silver nanoparticles with antibacterial action in some consumer products already. They're in socks, of all things. They're in air fresheners. They're in food storage containers. This stuff isn't regulated yet. I think eventually it probably will be. On an upbeat note, some of us may remember the old days where people who were on the beach, especially lifeguards, would have white noses. That's because they had zinc oxide on their nose to protect themselves. Now we make those particles smaller. They're nanoparticles. And you don't see them anymore. They're clear. And according to the Environmental Working Group, these nanoparticle sunscreens are environmentally reasonable. As far as we know, they're safe in terms of health. So this is a win so far. Now, thinking more ambitiously, you've heard a lot about the need to get carbon dioxide out of the atmosphere. You notice here we have a circle. You've got carbon dioxide in the upper left. Using these atomically precise catalysts, made with nanotechnology techniques, for example, by Christian Schaffmeister at Temple University. You can recycle that carbon dioxide back into a fuel. A synthetic fuel, burn it again, it becomes carbon dioxide, you recycle it right back into a fuel again. So this is an ambitious goal, but I think we're going to get there. Another early application that's coming quite soon is filtration. Sounds kind of boring, but it's not. It's pretty exciting stuff. If you look at that picture at the top, you're trying to get those red things out of that solution by running it through the filter that's green, and it's not working. You notice some of these red ones are sneaking through. It's not working well enough. But using atomically precise, single molecule thick membranes, using molecular precision, in principle, you could filter anything out from a fluid. That would mean you could take salt out of water. So many of you are from countries that have serious water problems. Here in the US, on the West, we're having increasing water problems. We need fresh water. You could take toxic chemicals out of water. Interestingly, you can filter blood with this. You can get toxins out of the blood. Many of us know people who are doing dialysis. You could get rid of that. So there's a small company, Aguavia, that has been funded by a couple different government agencies to look into this. And any of you who want to look into this filtration technology can talk with me. So these last two applications, the catalysis and the filtration, these are early uses of these atomically precise structures. Now we're going to look into the future. This is Singularity University. We're supposed to look ahead. We're going to look way ahead now and say what's going to happen over the decades to come. Where is this revolution going to take us? Well, the past revolution we've been through is the information technology revolution based on bits, the ones and zeros of software. That's the ultimate control on information. It gives us huge power in that space. We don't have that level of control on physical matter. We want to be able to control atoms the way we can juggle bits. It's harder with atoms. The rules are much more complicated. Bits come in two kinds, atoms come in dozens of kinds. Bits you can lay down in any order and they're perfectly happy. Atoms have all kinds of rules about the order and what they have to connect to. And if you do it wrong, they form all kinds of compounds you don't want. But if we want these benefits that I'm going to be pointing to, we have to learn how to do this, and we will learn. So what is this going to look like? Think about what a technological revolution looks like. Many of us have lived through part or all of the IT revolution, all the way from room-sized computers to PCs, to the early internet, to where we are today. I would bet almost everyone in this room, probably everyone in the room, has a smartphone. That smartphone has more computing power than all of NASA had when they landed the first men on the moon. So you've seen a technological revolution and what it means. It takes decades, 30 to 40 years, to really play out. Now, nobody predicted all the ramifications of that revolution, but some visionaries did pick out a few key things to deliver. And so we're going to take a look at what some visionaries are saying about this one. This is a design. Now, none of the things that I'm going to show you now have been built yet. These are designs, okay? These are future plans. So this looks kind of mechanical. It's a design of a hydrocarbon bearing that's made out of carbon and hydrogen. That center part turns around. It's a machine part to make very small machines. These are gears. You can see they would roll, right? You can see that we have a gear, we've got bearings. Where are we going here? We're going to make very, very small machines. Now, this should remind you of something. There are very small machines in our bodies. Biology does this all the time. We want to do it, and we want to do it even better. So now we're going to build something. The bottom right, we're going to add a carbon to that. So we have to build with atomic precision. Watch this. This comes in. Watch it transfer. First, it's going to pull that white one off. That's a hydrogen. Now it's going to go away. New one's coming in. All right, now see the black with the two white. That's a carbon with two hydrogens. Here we go. And it's pulling off, and it's gone. Now we have to finish it off. We need one more hydrogen. Here it comes in. Hydrogen transfers. It's gone. So this is the kind of construction you have to do if you want absolute atomic precision. You have to use like a tiny little robot arm to come in and deliver those atoms exactly where you want them. If you have this, what can you do? Well, the first thing you want to do is make another set of tools. You have to do this in parallel in order to ever get anywhere, right? To make a macroscopic object, you really have to move fast. So you have to have a lot of parallelism. So we're going to zip through a few designs. Here's a universal joint. You have one in your car. This is one of carbon and hydrogen. Here's another one with nitrogen and oxygen on the surface. Now, we talked about carbon dioxide. Let's manipulate it. Well, watch this. Okay, it's pulling down. Here comes the carbon dioxide. That shuts it off. And now you've pulled it out. You've pulled it out of where it was. Now we let it go because we're just doing a demo. So getting individual carbon dioxide molecules out of where we don't want them. Here's a molecular filter design. It's getting very complicated here, right? But you in your bodies are complicated molecular machines. Here's a very complicated one. It's a planetary gear. Again, you probably have one of these in your cars. It's cut away so you can see the inside. Every color there is a different type of atom, right? All right, let's look at some examples. Why would you want this? What's the benefit of atomic precision? We're going to look in 3 areas. We're going to look at computers, space, which we just had a great session on, and then health. So a new paradigm in energy efficient computing, millions or billions of times more efficient. That's energy efficiency. Let's look at some numbers here. If you look under the flops per watt, that's floating point operations per second per watt. It's a measure of energy efficiency. The yellow line is the molecular computer. The blue line is a very powerful Chinese supercomputer. And you can see that these calculations about molecular computers give you 10 to the 12th times better energy performance. That's 1 trillion times better. That's a revolution. When we can do this, we will have a revolution. You see the dollars, those are projections. I mean, the yellow line can't be built now. When we get good at it, these are projections on cost. They come way down. So that's computing. Very small, very cheap, very energy efficient. Let's look at space now. We just had a great session on space. What does this mean for space? Now, we know in space, getting things off the planet here, it's all about the weight. It's about the mass. So these super strong materials that are coming from molecular nanotechnology should make a huge difference, and they do. So every time I give this talk and I have to present this, I call up the technical folks and I said, are you sure? This is very counterintuitive, and they assure me, okay? So I'm going to present this to you. It's going to sound like science fiction. I'm sorry, this seems to be real. Okay, 4-passenger vehicle weighing 3 tons, including fuel, using nanotechnology, to take 4 people into space, including luggage. They always mention that. So the liftoff mass of this vehicle is about 3 tons. The cost, obviously this is longer term, estimated about $60,000. So 4 people into space, total mass of the vehicle and everything else is 3 tons. The vehicle itself, you see, is only 60 kilograms. That's what happens. You get a virtuous cycle. The less weight of the vehicle, the less fuel. The less weight of the vehicle, the less fuel. It's the opposite of the vicious cycle where you add fuel due to the weight of a vehicle. So in our thinking, how do we think about this? On the left, this is the traditional way we think about space. Huge vehicles, very heavy, immense amounts of fuel. According to these numbers, the one on the right, that's a traditional today's pickup truck. It's about 3 tons. So the weight of these projected vehicles to take 4 people to space would weigh the same as that pickup truck and cost not that much different from your family car. This is a revolution. I can't wait. Okay, so moving on into even more realms of science fiction, you look at this date on here. This was earlier this month. Thought-controlled nanoscale robots in a living host. Okay, this was published in a journal. The work was done in Israel. What in the world is this? Let's look at the abstract. You don't read this. I'll tell you the cool part. Mechanically actuating DNA origami robots tethered to metal nanoparticles. They get activated by a cognitively straining task in this animal model. In other words, these things are in the brain. This animal is attempting to think hard. It activates these origami robots to release their payload or to carry out some function. If this isn't science fiction, I don't know what is, and this is happening now with nanotechnology, right now. Okay, so for me personally, watching all this over the decades, I would like to see us work on extending the health span. Not just the lifespan. This lady here is 95 years old. She's had a great lifespan, but she is not in good health. When we say health span, we're talking vital, healthy lifespan, truly youthful health. Now, a lot of work is being done in biotechnology right now to do this, but with really precise control down to the molecular level of the structure of matter, in principle, we can fix any health problem, and that would certainly include aging. Now, there's a revolution. I hope we see it in our lifetimes. So how do we get there? You see where the yellow label is, that the arrow, it says medical nanodevices. We are over on the left. We can take a winding path and end up with some really great intermediary products, and that's good. But if we want to get to medical nanodevices as quickly as possible, we want to take the green path. It leads directly through this center oval called nanofactories. That's a general purpose ability to build with atomic precision. That is the fastest way to get these medical nanodevices. So I know folks who are working on this. There's even a company. So if those of you who are into corporate efforts, I can put you in touch. So I have a couple more minutes, and I'm going to do a physical demonstration. Here's something somebody may ask you about nanotechnology. One thing I didn't have time to cover is that with nanotechnology, you can have shape-changing materials, okay? And shape-changing products. These are made of molecular machine systems. Basically, they're roboticized at the very smallest level. You've seen videos here at the conference of robots moving around. Imagine that all the way down to the atomic level. So here's a question you may be asked, and I'm going to give you a demonstration, and you'll never, I think, forget the answer, okay? How fast, the question is, how fast can these things change shape? That's a good question. You could run a bunch of calculations, but I'm going to do a demonstration, and then you'll know, okay, it's at least that fast. Now, my body is made of molecular machine systems. That's what we are all made of, right? Tiny little machines. They're kind of floppy and watery, but they're machines all the way down. So here's my demo. Let's say you had a chair and you want it to be a table. How long is that going to take to do? Anybody want to guess? You don't have to guess. It's okay. It's not a test. All right. I'll do the demo, then you'll always remember. Okay. I'm going to take a system of molecular machines, which is me, and first I'm going to be a chair, and then I'm going to be a table, okay? I'm a chair, right? How long is it going to take me to be a table? Watch this. Okay, I'm a chair. I'm a table. I'm a chair. So the answer is real fast, right? Under a second. And I'm not even optimized for speed, right? I'm optimized for all kinds of other stuff. So when people say, well, how fast can nanotechnology products, in principle, how fast can they change shape? The answer is real fast, real fast. Think of it like a cheetah, at least. Any living system, these things can do at least that well. On that note, I think I'm going to close. Thank you for attention, and I've really enjoyed talking with you. Thank you.